Let's look at example 17.7. We have a 100 kilogram beam BD shown is supported by two rods having negligible mass. So we're only looking at the mass of BD. Determine the force developed if each rod at the instant theta equals 30 and omega is equal to 6 radians per second. So this thing is swinging down and to the left. First of all, we could figure out, does BD rotate? And there's two ways. One, both of these are on circular fixed radius paths. If they're both translating on the same radius path, then it's only a translation and there's no rotation. We can also look at the instantaneous center of zero velocities. If we drew the velocity vector at that instant, those would be tangent to the path like this, and they're parallel to each other, meaning we can never have them intersect and the perpendiculars don't intersect, or once again we have no rotation. So let's figure out what the acceleration of g is. If we're given omega for each of these rods, then the acceleration of B is going to equal to the acceleration of D. It's going to equal to the acceleration of G. They're all going to be the same since it's not rotating. And we can calculate that as omega squared R. And we can get an 18 meters per second squared. What acceleration is that? That would be the acceleration in our normal direction. So we're looking at normal and tangential components here. If I want to draw a Freebody diagram, I would have a force at B, we'll call it a tension, and we would have some tension at D. At the center of gravity, we're going to have mg pointed down, and these are going to be on circular paths. Helps me to draw those out. Then we can draw the components of the acceleration. We have a acceleration of B in the tangential, which is going to be the same as G, which is going to be the same as D. And we have an acceleration of B in the normal direction. Alright, well, we just found the acceleration of G in the normal direction, and that is 18 meters per second squared. So hold on to that. Next, let's take this Freebody diagram and turn it into a kinetic diagram. So all of those forces are gonna give us some acceleration and some alpha. Alpha in this case is 0. But here's our curved path through G. We're gonna have a acceleration of G in the tangent direction, an acceleration of G in the normal direction, and that'll give us our acceleration vector when we add them together. Okay, we know one of those, we know the normal component. To find the force, let's sum the forces in the normal component first, so in the normal direction. I have a TB pointed up, I have a TD pointed up, a minus mg cosine theta, which is 30 degrees, and that's all going to equal mass times the acceleration at g in the normal direction. We know this, we just found it, we know the mass, so that eliminates us down to two variables. We still need another equation. Let's sum the forces in the tangential direction. We have just the component from the weight of the beam, mg sine 30 degrees in the negative direction. and that's going to be equal to the mass times the acceleration in the tangential direction. Alright, we can calculate the acceleration of g in the tangential direction now to be 4.905 meters per second squared. We're still not done. Let's sum the moments about g. And we know it doesn't rotate, so that's our I alpha is equal to 0. We have a negative TB cosine 30, and that's acting 0.4 meters away. And then we have a positive TD cosine 30, and that's also acting at 0.4 meters away. They're just in opposite directions, and that equals 0. From that and the other equations, we can find out TB is equal to TD is equal to 1,320 newtons. Alright, you wanted to know the acceleration. We can plug back in and find that, or we have it, the acceleration in the tangential is 4.905 meters per second squared. We have the acceleration in the normal direction. Found that right away is 18 meters per second squared. From the geometry, we could figure out what our acceleration vector is, what the magnitude is, like any other vector.